Yeah, thanks for the introduction. Yeah, I'm sure you have heard about these developments where they build these massive language models like GPT or Palm or Chinchilla, which they have like billions of parameters. And so you might ask, how in the hell do they even train such large models? And one trend I see is that now JAX is gaining more momentum to build these large systems. And so my presentation will be about JAX, but also several software packages surrounding it to help you get the most out of this software. So this is roughly the outline of my talk. I'll first just briefly introduce JAX, and then because it's a functional programming paradigm, I will next discuss Haiku, which kind of allows you to be more modular and reuse stuff, while also playing in the JAX field where you have to be completely stateless. And then I'll just touch upon a few other packages which are useful for your day-to-day work. So what is JAX? Well, I think mostly it's just NumPy. It's NumPy, but it has extra capability to make linear algebra fast, and also it has the opportunity to take derivatives. So in a sense, this is it. And one of the things that makes JAX so fast is that you can also compile things, so to just-in-time compilation. So if you are familiar with Numba, JAX can also be compiled. But what makes it slightly different is that you can easily, after compilation, you can run it on GPUs, you can run it on TPUs, so you get this portability for free. And what makes it useful for training these large language models is that it's scalable across multiple devices, multiple hosts. So it can trivially be scaled out across multiple machines. So in a nutshell, think Pytorch or TensorFlow, but conceptually it's much simpler in that you have to write less boilerplate code, and it's much closer to the math compared to these other packages. And one key difference between lots of the other software packages is that it's a functional programming library, and we'll talk about that in a bit because I think that is important to keep in mind. And the too long didn't read version of my JAX slide is that there's this NumPy, and it adds three components, three functions really. JIT, just-in-time compile your code. Grad, to take derivatives of your functions, and vmap, factorized map, which allows you to write one function and then execute it on multiple elements in, let's say, an array. So it's a factorized version of a map. So I think we should pause a little bit at the functional programming side of JAX. And what does it mean, functional? Well, really, it means it looks like a mathematical function. So if you look here at the sketch, something goes in, for example, x. Then you have a pure function. And what does a pure function mean? It means that nothing can go outside or inside this box, which I call pure function. And then something goes out. So really, like a mathematical function, something goes in and something goes out. And for example, if you have a neural network, then your pure function would be this neural network where the input features go in and the weights of your network go in, and then let's say a prediction y comes out. And what is important to realize is that this also has large implication for taking random numbers, because there's no longer a global state to keep track of your pseudo-random number generator key. So now you need to explicitly pass in the pseudo-random number generator key into your function if you want to take random numbers. So this looks a little bit abstract, so let's take a look at a few examples. So here I have a simple function. So to use JAX, you just import, instead of import numpy as np, you just import jax.numpy as jnp, and then use stuff as you would normally do in numpy. And here's a function. It prints x and then takes the sign of x. So I'll give you just a few seconds to think, is this a pure function, yes or no? No, it's not stateless. Why? Because it has a connection to the outside world, which is the standard output pipe. So not everything that is in this function is completely confined to this space. So it goes out to this function to connect to the standard output pipe. So in theory, if you would pass in the standard output pipe, then it would be more pure. So here another example. I pass in the x weights and biases, and then I do just a linear transformation, and then I return this result. So do you think this is this stateless? Oh, pure? Yeah, yeah, exactly. This is right. And so maybe this is another example. Third example, we have x and we just shift it, and then return the value. Does this look stateless? No, exactly. So the bias is outside this function, and for example, if you would compile it, then it will compile out this constant. And so what would happen if you change, for example, the bias, then it would to, let's say, to some different value, then the bias in this function is still cached. So then, yeah, it would behave not as zero would expect it. So this is, I think, an important part to keep in mind. Why? So why do you want to have stateless programs? Well, essentially it means that you can just put everything together and then just give it to a specific device, and then it knows what to do and doesn't have to communicate to outside. So that is one of the reasons they do it like this. And so here's an example where we just in time compile the function. So here's like essentially like a smoother rectified linear unit. And yeah, this is just some function which you can then calculate. And here I just also want to show you how much faster compiling is using JAX. So we take here just a large array. So here I generate random, very large random numbers. It's not important that it's normally distributed, but I just need something large to make the timing slightly more reliable. So an important difference that you can see here is that for JAX you always need to pass in the pseudo-random number generator key, so that you can see here in order to generate numbers. And so by just calling this by JIT around this function, JAX will compile your function. So what it will do is it will trace your function. It will, when it runs first, it will see which functions are hit, and then it tries to fuse together operations and do clever tricks to make it more speedier. And here you can see it's like an order of magnitude faster just by calling this JIT function around this function. So it's quite easy just to get a large boost of performance. So that is the first part. So I said there are basically three important things: JIT, grad, and vmap. So grad is the second element that is new on top of NumPy, and it allows you to take a derivative. So here's a simple second order polynomial. And so if you put in 1, then yeah, as expected, you get 1.5. And now to take derivative, it's quite easy. You just use the grad function of JAX, and then you have a new function, which is now the equivalent of the derivative of your polynomial. So if you take the derivative, then of course this 2 cancels with the half, and the x becomes 1, so then it is 2. And you can even take second order derivatives, third order derivatives, as many as you like. It's just you redo the operation, and then you get higher order derivatives. The third new thing that JAX adds is automatic factorization. So here I will give you an example where we initialize some weights where we do simple weight times x a multiplication. But here in x it's batched, so we have 10 in the leading axis, 10 and 10 batches, and then we apply these weights to this batched x. And if you would very naively write this batched version where you do this for each batch, this multiplication, then you would, for example, write a loop like here. So this is a list comprehension where we take out the element of the batch and then apply it to this function, and then stack the results along the first axis. And JAX allows you to factorize this very simply by using, instead of writing this loop, you just use vmap to map this function along this first axis. And so here you can see it's like 2 orders of magnitude also faster by compiling it and using the factorized map. And so this allows you to focus really on the key computation that you want to do. And if you want to do this for multiple batches or along multiple dimensions, then you can just do vmap and you don't have to think about all the shuffling of the indices to keep it right. And what is also nice is that you can also pmap, so that is a parallel map your function, and then you can do this single calculation, for example, on different devices. So it's very easy to split up your workload. But there's of course much more, and we don't have really time to go in all the details. But I already said that you can shard your computation across multiple devices, and you can also split the memory of, for example, of your arrays, split it up across multiple devices. So this is shown here. That let's say you have a matrix, and you can say, okay, this part I want here, that part of the matrix I want there. So if you have a large language model, then you slice up your large numbers across multiple devices, and when you do calculations, then the new parameters are then automatically inferred what device it should reside to minimize the crosstalk between devices. And there's an entire language called JAXpressions, which essentially is the compiled version of your JAX code, which you can really see what's going on, what has the compiler done. There's tools like Perfetto to profile your code. There are special debuggers, not only you can just normally execute like in NumPy your Python code and jump through them, but if you compile your code, you can still use JAX debuggers to see what's going on, even though you have compiled and fused perhaps together several operations. And there's a concept called pytrees, which is essentially, well, I think the description given here is perhaps the most succinctly description of it. So it's a container of leaf elements and or more pytrees. So it means either it's a leaf of the tree or it is a part of the tree. And this is very natural if you have nested structures like neural networks, where you have neural networks also have like this tree structure where there are different dimensions as you go on. And PyTrees allow you very naturally to map also over the first axis in this tree. Okay, so this is it for JAX. I will now continue with Haiku. So Haiku is the element that is built on top of JAX. So as I explained, JAX has to be pure. It has to be stateless, and that means that reusing components is much more difficult. So you cannot directly use the object-oriented programming paradigm in JAX, and Haiku is a way out of it. So it allows you to write really blocks of reusable code, and then you can reshuffle and compose them, all these elements, very neatly. And so, for example, if you have a simple one-layer network, then you can imagine a larger neural network is just several components of these chained together. And Haiku is a way just to make this modular. You just say, I have this one layer, and then you can reuse them in an object-oriented way. And Haiku is a way to turn this object-oriented, this stateful program, to make it back into a pure program. And so to use it, there are three key steps. And it is a transform, which first you define a function with your components. Then you transform it into a pure function. Then you run init, which is a way to initialize your function. And when you really want to use it, you use apply. So we'll see that in action now. So here, for example, is a multi-layer perceptron. So this is a network of 300 by 100 by 10. And here we just apply it on these input features. So the first step is to transform it. So in this multi-layer perceptron, there's all these weights and biases of this network. But I told you it has to be a pure function. So Haiku.transform turns this function into something that has all the parameters back into the function. And the second step is to run init, which is a way to initialize the network. So here I just take some input features. It doesn't matter what it is, but you pass in a pseudo-random number generator key, and then you can see on the right. So this is the Py tree. So a Py tree is a tree-structured form, and here you can see all the weights of the network, and it was initialized using this pseudo-random number generator key. So the W of the first layer, the weight of the first layer, the bias of the first layer for the second layer, and so on. And so finally, now that we have transformed it into a pure function and we have initialized all the parameters, now we can use it like a stateless function. And this is with apply. So you pass in the parameters, which makes it a pure function, and a pseudo-random number generator key should your function use random numbers, and the actual argument x. So this is the first argument of your function. So this all these three elements allow you to combine the object-oriented programming design with JAX. So Haiku allows you also to build your own modules. So let's say I want to partly reinvent the wheel. Then I can define my own module by just inheriting from Haiku.module. And here you just specify for this linear function the number of hidden output units of your linear transformation. And then you specify your underscore call. And in this network you have weights and biases. So you specify .get parameter to specify the parameters. You also need to indicate the shapes of your parameters, because of course it doesn't know it by itself, and a way to initialize it. So here w_init is a way to initialize using the positive numbers of a normal distribution. But you could also initialize it, for example, using zeros. Well, then how do we use it? Yeah, the 3 steps I told you before: the transform, the init, and the apply. So first you transform it using the decorator haiku.transform. And then we also add the decorator without apply random number generator, because the linear transformation is deterministic, so we don't need random numbers. Then we initialize the function, and so here we can see these are the w and the b, which we specified earlier using haiku.get parameter. And then finally, to use it, we just run this function.apply, and then we pass in the parameters of our network and the function we want to evaluate. So this is just to give you an idea how to use this composability in Haiku in JAX. But in addition, Haiku is also just a library of several components that allows you to mix and match several things, like multi-headed attention with a dropout layer or a linear layer. They even have complete networks like ResNet with pre-trained weights. So this is already all in this library, and you can just mix and match all these components in a very natural way. In the last few minutes, I just also want to sketch the larger ecosystem surrounding JAX. So we also have JAX, which is basically a way to write unit tests for JAX, and it allows you to have different variations, compiled versions and non-compiled versions that you can automatically check. Fake environments where you have multiple devices while it's actually just runs on CPU. All this kind of stuff, which helps you just to check if everything looks as it should. Optex, which has a bunch of optimizers if you want to do gradient descent optimization, so like stuff like Atom optimizer or ARMS probe or stochastic gradient descent. All this stuff is in Optex. What I find really lifesaver is tensor annotation. So if you have, for example, videos, then you have multiple indices which semantically mean different things. And for example, they can refer to time, to the width of the image pixel, the x or the y coordinates. You can also have multiple batches of videos. And so you sometimes can confuse the different indices. And tensor annotations is really a bookkeeping tool where you using Python type hints, you can check the consistency of your indices throughout your code statically. So it's really, you can see if you have, for example, swap two of the indices using by running mypy on your code, and it says, okay, yeah, the type annotations don't check out, so there must be a mistake semantically, even though it may just run fine normally. And finally, there's another library called Flags. So it is also a neural network library like Haiku. It has what they say batteries included, so it also has some optimizers. And conceptually it's similar to Haiku in the sense that it tries to give you modular components to be able to reuse stuff in JAX. And this brings me to my conclusion of my talk. So we first introduced JAX, and it is a way to do a linear algebra and a numeric computation fast, and it also gives you gradients. And an important thing to keep in mind is that it's a functional programming paradigm. And Haiku is on top of JAX and allows you to work in an object-oriented way in this purely functional paradigm. And finally, we just briefly sketched some of the other packages in this ecosystem which help you to maximize your productivity using JAX. And this is it for me. I would like to thank you, and the floor is, as far as I'm concerned, open for questions. Thanks.
Thank you, Hylke. All right, anyone have any questions? We'll start in the front, in the green.
Yeah, thanks for the good talk. Do you know of, so for example, a benchmark model like ResNet, do you know of any comparison the speed of trading and inference as compared to Pytorch or TensorFlow?
Last time I checked, it was I think quite a bit faster, but now Pytorch 2 has been released, which claims to be in some certain cases outperform both JAX and TensorFlow, but at least yeah, it's, I think roughly speaking comparable, but in certain cases it's faster than these competitors.
Okay, but not an order of magnitude, let's say.
No.
Yeah.
Anyone else? In the green?
Yeah, so I was wondering, you give like pseudo-random number generated key sequences, right?
Mm-hmm.
And like from the standpoint of reproducibility, right?
Yeah.
To really ensure that the network reproduces every time again.
Mm-hmm.
It is known that, for instance, really physical hardware sometimes does not reproduce certain number sequences correctly, right? So does JAX make any guarantees about reproducibility in this sense? Because with these key sequences, it seems to be like really focusing on trying to keep everything as consistent as possible, but maybe you know something about that.
Yeah, as far as I know, it should be reproducible in software sense, but if there's some hardware failure, then I don't think they guarantee this kind of stuff. No.
In the white, in the back?
Actually, I have two questions. The first one is in terms of packaging with Pytorch, the interaction with CUDA, and everything in VIA related is sometimes difficult in terms of what version to install with what. What's your experience with that, with JAX?
Yeah, I think similar. yeah.
And with CPUs? Have you worked with CPUs?
No, frankly, I have not.
I guess that's easier because it's like a Google product, right?
Yeah, I think so.
My second question really quickly is, could I just plug in JAX where I use NumPy normally, or you don't see any cases where maybe the NumPy library has functions that are not supported or anything?
I think there's only like a handful of functions which are not ported, but it also has SciPy implementations, and so I think the basic difference is that if you want to draw a sample random numbers, then you have to pass in the key. So this is only the real difference, and otherwise you just replace an NP by JNP, and then you can compile it, and then you're just fine. So that's it. So it's very easy.
I believe there was one. Yeah, there.
Related to the previous question also, if you have the JAX NumPy data structures, for instance an array,
Mm-hmm.
then also pass it to libraries that use NumPy internally, not the JAX NumPy.
Yeah, so you can use it back to in NumPy. So you can pass in NumPys for JAX, but you can also collect it back to NumPy. The only thing is that you have to wait sometimes a little bit, because then all the data has to flow back from the GPU back to the CPU, and so it goes. The calculations are asynchronously, so it will continue calculation, and then it gives you back the interpreter if you're in a notebook. But if you want to fetch it and see it on the output, then it has to go back from the GPU to the CPU. So
is that a manual operation or?
No, it's automatic. Yeah.
Anyone else? Yeah.
So one really nice feature Pytorch is that it has really great data loader support. So it's actually quite easy. Loading your data is often a really big part of the code base.
Yep.
Does JAX have similar
No.
mechanisms?
No, so it tries to be just basically NumPy but fast. So all this stuff, they write additional libraries for this, but they try to keep it apart from JAX itself. So they really try to focus on the core NumPy components and the acceleration you can get from this.
And Haiku, does that have it? Or is it a different package?
I think I don't know actually. Yeah, good question. I don't know.
I'm sure there is something.
Yeah, surely, yeah.
All right. Well, that concludes this talk. Thank you for talking and speaking. We have a gift for you today.
Thank you.
And catch up with Hylke afterwards for any of your data science questions. And enjoy the rest of your day. Thank you. Round of applause.